I am speaking for Jos Fringe and Lydia Venvacarida Lirugia from KWR. Unfortunately, they were not able to make it today as they had other engagements, so they asked me to present the NextGEN project for them. I happen to be a senior researcher working in the University of Exeter in the United Kingdom, and I am obviously not the coordinator of the project. I'm a computer scientist by trade. So if you have very technical question about some water technology, I will encourage you to redirect this question via email to either Lydia and Jos from KWR. I will, of course, be able to answer as much as I can with what I know. All right, so the NextGEN project is a fairly big European project, which is about circular economy. It tries to focus on the three areas of circular economy, which are water, energy, and reuse of materials. Now, this is interesting in the sense that there are 10 diverse case studies, which are all around Europe. And there is quite a mix in there. For example, some of them are in the Netherlands. They're fairly state-of-the-art, edgy technologies. Some other are focused on more traditional technologies, but the implementation. Or we have also a variety of cases which are more about the communities of practice, not so much the technology itself, but how to connect with the people and make sure that the circular economy, the message is going through. For example, we would have Gotland, which is a little island near Sweden, which is very, very dry because there's not that much rain going on and there are many tourists coming. Weirdly enough, we have Costa Brava, which is, well, in a very similar situation, but in Spain. So there is quite an interesting mix of things going on in there. So yes, there is quite a wide array of activities. Stakeholders and end users are involved. There is all sorts of frameworks for the integration and the demonstration of different technology. I am more interested personally, because that's where I'm working, into the engagement of citizens. So there are living labs. I have been in charge of developing a serious game related to circular economy of water. And another part of the project has developed an augmented reality app in which you can walk around Athens or anywhere, and you can have special places related to circular economy. So it's a bit like a treasure hunt, a little bit like Pokemon, you know, this game in which you have to walk around. And then you have to find information, and you can change with the slider some of the object that appear on your phone. There's also a part of the project that's concerned with governance and recommendation related to it. There is also quite a substantial activity related to partner transfer of technology and partnership. And it is also linked to a digital marketplace that's been developed where different technical solutions can be accessible for different members of the industry. The general idea of circular economy for water touches many domains. So it can lead to, electricity, production of goods, and water quality, and all sorts of cycles, and sometimes cycles which are outside of just the limited view of the water cycle itself, but more like at a higher level. I'm gonna look briefly at some of the case studies because I do not remember or know all of them very well, being more on the serious game development, but I'm gonna give you my view of what I learned in some of these case studies, something that's not written on the slide. For example, something that's fairly interesting, La Trappe in the Netherlands has this idea of, this is a brewery, which is held by monks in a monastery. And they contacted the aerospace agency to make a brand new system to filter and purify the water that comes out of the wastewater that comes out of the brewery. Now, what's interesting, there is not one single moving piece. It is a row of trees with tubes, tubes made out of special materials, which are wrapped around the roots of these trees. On one end of the greenhouse, you got the wastewater that comes in. And on other hand, once this water has gone through these different roots, the wastewater comes out clean and treated. And they use communities of bacteria that have been modeled via computers to work together to purify the water. So what's interesting in that particular example, it's something made for astronauts to live in space, like a contained system to filter the water using exclusively plants and microcolonies of bacteria working together, has been used to produce a pretty good working prototype. And that's basically being implemented. So this is one of such example, and I cannot go through the lens of all the different specific case. I know that you've got 3 types of color on this slide. And if I try to minimize that, I think when it's yellow, it's about energy and heat recovery. So for example, in Athens, there is a program in which they're trying to recover heat from wastewater and at the same time produce some fertilizer. And also with some of the partially treated water, use it to water some park areas. So we got this, wide variety of cases. So overall, I mean, the goals are kind of similar to what's been talked about before. The optimization of water resources, the reuse and the mining of nutrients, and trying to attain this positive state of energy generation, where not only you limit the loss of energy, but you actually try to create more energy. So the overall stakeholder engagement strategy has gone pretty much all over the place. I mean, communities of practice, I spoke about Gotland, which is this little island where there's this, drought problem, but also Costa Brava. And we are going to use the serious game, for example, in the case of Costa Brava, to show a classical example of a Mediterranean case study in which you've got limited resources, the tourism season come in, and you got to manage your aquifer. And if, for example, the level of water in your aquifer gets too low, then you got salt infiltration, and then you got all sorts of problem coming in, and the different regions or community need to work together. So we have, because of the pandemic, of course, lots of it has been slowed down, but at the same time, it's accelerated the development of the serious game because we're relying on it as an online tool to reach more people. So the added value overall, it's the demonstration that we can scale some of the technologies which are being analyzed in this project. That some of them are actually ready for exploitation. Not all of them. It is not, guaranteed that everybody can afford the aerospace technology. But it's kind of interesting to see it work, and perhaps it paves the way to the future of what wastewater treatment could be one day. We have a fairly strong program of engagement of citizen, but also even perhaps policy makers that might come out of a serious game. And we are also showing a little bit of work regarding business creation of opportunity with the marketplace, which will be a full online platform where people can show the products and the novel technologies, and where one can see what's on offer for solving problems related to circular economy. So these are all the partners. I can't even count them. I mean, there's a lot. It's all over Europe, and it's been an interesting work so far. But now I stop talking about the project itself, and I'm going to show you the serious game, at least the prototype that has been developed so far. So can you see my screen, and can you see the browser?
Yeah, we can see it.
Excellent.
Yeah.
Thank you very much. So this is a game that will be accessible on a website that everybody will be able to play from. It's designed to play from a laptop or from a tablet, possibly even from a mobile phone, but the optimal design would be from either desktop or laptop. So this is just the introduction of the game, but it will be online. Once you've pressed the OK touch, you're driven in front of that screen. So what's happening in there is there is two things. There's what you're seeing just in front of you, and there's what's going on underneath. What you're seeing right there is a toy town. We call this model Toy Town. It's a small catchment of 600,000 inhabitants. So not so small, but quite representative in size. And what you're seeing there with my mouse in purple is the reservoir. So the reservoir supplies water to the river to make sure you've got a working ecosystem, but also to the town. And the little blue box that you see here is your drinking water treatment plant. You've got three types of neighborhood in this town. One neighborhood that you see on the left, type B, has got all sorts of fancy technologies linked to circular economy of water. It recycles a portion of the water, rainwater roof harvesting, reuse some of its water in the toilet, for example. It also has things like fancy toilets. It has different types of technology, and it's linked to what is called sustainable urban drainage system, which is some sort of basin that acts as a dampener. So when there is a flood, it kind of contain a bit of the water to make sure that your central wastewater treatment plant is not overcome by sudden influx of floods. So the other type of house, house type A, is actually a normal type of house where all the gray water and the black water are going straight to a central wastewater treatment plant. And finally, we got another type of neighborhood, neighborhood type C, which is connected to a secondary wastewater treatment plant. So that can be used to for other effects that I'll describe in a few minutes. So all that is there is the rainfall, and there's all sorts of parameters linked to energy and to material reuse and all that in the background. This goes in principle to a circular economy score, which is at the top. Notice that this is still a prototype, and at the moment, the circular economy score changes at random. But what's happening is behind all that, if I click on one of the components, there's a lot going on. For example, this was the reservoir. The reservoir's capacity has got a threshold, and it's simulated on a daily basis for all the data we got and simulate over 60 years. Now, what's interesting is normally when you build a system dynamic model that needs to give you result in the water area or in research related to water, usually you can compute that in a few minutes, but when you're trying to make a serious game, the result needs to be instant. You need to get your result in less than a second. So if I change something, let's say you got your stressed reservoir, and if I was to whatever I decide to discharge in the river, I decide to discharge a lot more in the river. Instead of 40% of the outflow, I let a lot more go into the river. I compute, and you should see that there is a change happening right now. So you can see the previous phantom diagram, and this is the new result you get. So everything in the background changes, is computed for the next 60 years on a daily basis in less than a second. In order to reach that, we had to get out of the standard programming language like Python, and we had to use some newcomer called the Julia programming language, which is very similar to Python, but has a higher speed like the C language. So this is probably quite technical, but it's just to say there is a lot of things going on in the background. It's not just a nice interface. There is all sorts of things being simulated. And what you are presently seeing is actually an old version already, because we have added a lot more to the model. So let's just refresh the screen, because it's a browser-based application. So we could just restart anytime. So you're starting there with a fairly stressed reservoir. I mean, not that stressed. 30% of the time, your reservoir is less than a certain percentage. Let's say less than half. That means it's considered as stress. And then your water demand is basically when your reservoir is not empty. If one day in your year, your reservoir is empty, that means you cannot satisfy water demand. So what would happen is if, for example, you look at your population and you decide to increase from 600,000 inhabitants, you decide to double it. You say, well, you know, global warming, perhaps lots of cities are getting emptied somewhere and some other cities receive more people than they should normally receive. And what would happen if I double my population? So what happens, I just put the slider to the right and suddenly lots of things went red. Your reservoir is now under stress, and also the E-flow, that is to say the environmental flow in your river, is also red, and you've got a certain amount of untreated water that comes downstream. So you got, you know, three problems. One problem is because your population has increased, your water demand has increased and cannot be met with what's going on at the present moment. Then your environmental flow that goes for the river is a bit in crisis. And finally, you're discharging far too much untreated water at the bottom of the river. So what can you do? Well, you have to explore the different components that are available. But one of the things you can do is you can start wondering if there is a way to decrease the water demand. What about increasing the percentages of houses that use circular economy kind of device, like, you know, these special toilets that use less water, or this special roof water rain harvesting technology. So if I put the percentage of this type of nice house there, you suddenly see a change. Now you meet 80% of your water demand instead of 30%. So it's not that you've completely negated the problem posed by having your population doubling, but you are kind of mitigating the problem. Now you still have a bit of an issue because, for example, here you have a big disparity in the untreated water you're letting go downstream. So there are different ways with which you can act. For example, you might decide to increase the percentage of houses which are connected to a secondary wastewater treatment plant. And if you do that, then the untreated water, if there is any, will be dumped midstream. So instead of increasing your concentration of untreated water at the same point, you kind of spread it slightly to create some, create less distress for the environment. So for example, if I take my percentage a bit lower and I increase the percentage here, we will start seeing that instead of being, green here and yellow there, they both become kind of less yellow and a bit more green. That means that we have kind of balanced a bit more the amount of untreated water that was coming through. There are lots of aspects to the problem. I'm just showing you a portion of it. This tool is quite useful to explain circular economy, and there's a lot of things in the background that are not necessarily detailed or functional yet, but I'm going to show you, if you want, some small overview. For example, exergy. So the trace amount of metal that comes to the wastewater treatment plant have a certain value. And more than that, because it's circular economy, they have a value beyond just the little town we're looking at. For example, if you were to recycle, the amount of aluminum you found in the wastewater, in the raw sewage, the traces of aluminum, then you don't need to go mine the bauxite to create aluminum somewhere else. You can just reuse that. And by doing that, you do not consume this extra energy you would need to consume by going mining and creating and refining aluminum. So just to give you an example, this is something we are adding at the moment, and it's not active just on that screen, but it's being added as I'm speaking roughly at the moment. So what's happening is if, for example, you manage to take 1 kilo of aluminum and recycle it, the amount you can save by not having to go mine it is the equivalent of a Tesla Model 3 running for 7 miles, just for 1 kilo of aluminum. So there are lots of extra things that can be looked at beyond just what is being shown here. Something we are actually planning to add. For example, these things are empty. We have a new version that is showing other types of information, but it's not ready yet. So I'm showing you the old prototype. But what we have is, for example, you're now able to choose new components, which components in each house you want to install. And we discovered something which is quite interesting. If you install, for example, a vacuum toilet, which is supposed to consume a lot less water, installing a vacuum toilet has consequences on cost, because you need to have a whole network of pipes with special vacuum pump, which is quite expensive. So you consume less water, but it's also costly from a maintenance point of view. And at the same time, because it consumes less water, that means that the water that is in the pipes, the sewer pipes, doesn't move as often. So you've got more corrosion as well. So you got an additional cost. And on top of it, because the water that comes is more concentrated, the COD in the water that comes to the sewage is higher. So that means that the water treatment plant has to spend more energy treating this highly concentrated water. So you think you might be saving energy by having vacuum pumps, but perhaps your energy bill is higher because the water treatment plant at the other end of the town will have to treat that extra concentrated raw sewage. So we got different models. So for example, you will be able to show people how you can compare having, in comparison to a vacuum pump, having a high pressure toilet, in which is the new thing that doesn't cost as much to maintain, but has similar result. So we hopefully will be able to show people a story in which they will be able to investigate each component. And of course, the scenarios that are going to come out of that are going to be quite merciless, because, for example, here we got our rainfall at 100%. But what happened is, global warming, climate change. What happened if you got 10% less rainfall? Well, we're going to see, or let's say 15% less. So I just moved that, and then up everything. The reservoir stress is now at 100%, and you can only satisfy 40% of the demand. And now you've got to find other ways to play with the components in the system, so as to optimize the result. So now this is a template for a toy town, a kind of generic town that we are nearly finishing implementing. You're not seeing the last version yet, but it's going to be available online for this summer. And we're going to adapt it to different case study. We got a case study in Greece. So for the Greek case study, we're going to take this generic toy town and we're going to add to it little bits and pieces, for example, heat reuse and fertilizer production from sludge. In the case of Costa Brava, which is the other case study we're going to work on with the serious game, we're going to add a desalination plant, and we're going to add on top of it aquifer management, so that when you let your aquifer level goes too low, there will be salt infiltration. So as a game, you have to be careful to maximize your score and not let the level of the aquifer goes too low. Similarly, we're going to add things that not many people necessarily consider, but things like, for example, if it's a touristic community versus an agricultural community, they both have water needs, but they will need to do some effort, and there will be some modification needed for the whole circular economy cycle to work. For example, in the case of the touristic thing, perhaps consider cases for the tennis grounds. You know, this brown earth tennis ground, they actually use a lot of water, convert them to some more synthetic kind of surfaces. Or similarly, for golfs, perhaps reuse gray water instead of consuming drinkable water to just water gigantic golf surfaces. See if there is a way to implement such measure inside the virtual toy town and see its effect. Similarly, see also the cost and the operational maintenance, if they can be shared between this competing community. So this is a template, and it's not super rich yet, but we are adding, as I'm speaking, quite a lot of things to it. And it's going to be quite interesting, I would say 3 months from now, because it will be available online to play with, and there will be a lot of things to derive from it, both from a general case study, from Athens case study for heat reuse and fertilizer production, and for Costa Brava, which will be a nice case study of a typical Mediterranean kind of problem.